Thank you. Yeah, it's great to be back in Hamburg after, well, 12 months essentially. I have a lot to talk about today, so I really don't want to bore you too much about my bio. So I will instead have my presentation glitch out right in the beginning. What's happening? There we go. So as Winfried was already mentioning, I kind of am a person that likes a tough challenge. Like early in university times, I was looking into video game console emulators. It was always mind-blowing to me, like how you could get games running on a platform that they were never intended to be ran on before. There was lots of stuff to learn about, lots of cool people to meet, and it was just an amazing experience. During uni, what I was doing instead was I was studying physics. I really wanted to go into academic research and research theoretical physics, understand how our universe works, you know, just everyday things. And there's a few funny pictures from that era. It turned out academic research wasn't really my thing. So what I ended up doing instead after uni was to get back to software development and join Imagination Technologies, where I worked on the Vulkan driver for PowerVR GPUs. One thing led to another, and I was doing the same kind of work, but for the open source Mesa project, where I was working on the Vulkan driver for AMD GPUs and on the shader compiler in particular. So also lots of valuable lessons. So after all of these tough challenges, we'll look at a different challenge today, and that's FEX. Maybe. Oh, this is starting out amazingly. I love it. There we go. Well, wait, not that FEX. There we go, FEX-EMU. So we're an x86 emulator for ARM systems. And actually, I wanted to get to know you a little bit here. So how many of you, show of hands, would call themselves gamers, whether casual or like really hardcore? That's a lot, okay. How many of you have like a technical background as a software engineer, for example? That's also a lot. I'm going to assume that's representative for the whole of Germany. Sure. How many of you, oh, this is going to continue like this, isn't it? How many of you run Linux devices? Here's the twist, though. How many of those Linux devices run on ARM platforms? Oh, come on, guys. Okay, I expected the number of hands to go noticeably down, and they went down with the last question a little bit, but not as much as I anticipated. So thanks, folks. Thank you. So what I was going to say is ARM devices are actually a little bit tough to get by. I mean, sure, there's Raspberry Pis, which I'm guessing most of you own. But like if you want to get a consumer laptop, like this one, for example, that runs on a Snapdragon chip, those are actually really difficult to come by because most vendors still base their hardware on x86, like AMD and Intel CPUs. But a few vendors are testing the waters. Lenovo is one of them. I think Dell has released an ARM-based model. And of course, there's Microsoft Surface, and I don't need to mention that Apple has ages ago adopted ARM for their MacBooks and other devices as well. So on Linux, we kind of have an easy time dealing with these big architecture changes because most of our software is open source, so we can just recompile the world whenever our hardware changes. What we can't so easily do is recompile proprietary games that we still want to play, or things like Photoshop or Office suites that we might need to use for work. So 7 years ago, Ryan Howdeck actually started out with the FEX project because he wanted to create a solution that is able to run this type of software on Linux platforms, even if they use this these new ARM chips. And me personally, I joined development around 4 years ago. So it's been a while so now, so I feel like hopefully I deserve being on stage here today to tell you about this stuff. If you're asking yourself the question, what actually is involved in emulating an x86 CPU, well, first let's look at the whole system that we have, because there's more to it than just the hardware underneath. On top of the CPU, there runs an entire Linux operating system maybe, thank you. A Linux kernel that does things like making sure that your game cannot read the passwords that are saved in your browser. It takes care of file system abstractions, and it bundles all of the device drivers. On top of the Linux kernel, we then have the various base libraries in your system, like the C runtime, the Java JDK, the .NET runtime. We have graphics libraries like OpenGL and Vulkan, and of course we have game engines like Unity or Unreal. And only on the very top of the stack we see the actual game, which free opportunity for a game developer to pick a really, really amazing name here, so don't miss out. If we look at what this all means for FEX, we're just going to ignore the middle layers for the time being, and just focus on what happens as far as the CPU is concerned. So the problem that we have is that the game expects to run on an x86 CPU, but we have an ARM CPU now. So that doesn't quite work out. What we can do, though, as an emulator is we can translate on the fly the game's binary code from x86 to ARM. And we do that using a tool called a binary recompiler, which, well, as the name suggests, it doesn't compile a high-level language program like C to assembly, but rather it takes existing assembly code and recompiles it to a different architecture from x86 to ARM64. What does it look like in practice? Well, here's some very simple toy example. The specifics don't really matter too much. I just picked 4 really simple instructions here. And the key here is we don't directly go from x86 to ARM, because that kind of munges together 3 different tasks. We need to decode the x86 instructions. We need to pick the corresponding ARM instructions that do the same thing. But then we also want to do this in a way that is really optimal, because we want to play, for example, games at like fluent frame rates, so we can't just turn one x86 instruction into tens of ARM instructions, but rather we want to have as close as possible to a one-to-one mapping. And for this, to meet this end, FEX uses what's called an intermediate representation, where each of the instructions is compiled to a group of FEX internal operations that have a very specific meaning, but the key point here really is that given this intermediate representation, we've done the decoding part, and we can now focus on the optimization part. So we can take our internal representation and make sure, like, do things like constant elimination, for example, to make sure that whatever code we use to ultimately generate ARM code is as minimal as possible. And this is much easier done on an intermediate representation than on x86 directly. And only after this step, we pick the final ARM instructions. And you can see, using this approach, we get fairly close to the original input assembly code as far as size goes. If we ignore the IR for now, I picked a slightly more involved program. Very simple loop structure here. And we see the ARM code gets a little bit longer than before. And I just wanted to take a moment to highlight all the different like fundamental issues that we're facing here. The first one is, if you like pause the video if you're watching offline, or just look at it later, you would see that most of the stuff up here more or less directly maps to the x86 code, but the bottom part is more or less overhead we just incur every time we enter or exit out of an emulated block. That is just something we can't avoid. We can make sure to keep this kind of static overhead as small as possible, but it's always going to be there, unfortunately. Another thing is this specific, I'm sorry, I should highlight it here, this decrement operation. You would think this just maps to a simple subtraction on the ARM side. You just take a register and subtract 1 from it. And indeed, we can find this instruction on the right side in form of the sub-s instruction. But looking closely at it, we also find that there's a CSET and an RMIF instruction, which You wouldn't expect that, but the reason it needs to be there is something that's called flag handling. So whenever you have arithmetic operations that add or subtract numbers, there's a chance that you're over or underflowing your number from like the 32-bit, from the available value space in a 32-bit or 64-bit number. And for this purpose, x86 sets flags on most of the instructions, even if the program doesn't actually ever read those instructions. But as a recompiler, we can't statically determine this usually, so we need to generate this corresponding code unconditionally. And it's only thanks to IRR that we can get a somewhat feeling of what the next instructions are actually reading as far as the flags are concerned, and then keep this code as minimal as possible. Without this kind of optimization, we wouldn't have 3 of these instructions in total, these 3. But we would have like tens or 20 of them. It's much more heavy, and we obviously don't want that. As far as so these are the fundamental issues that we're facing, but there's more pragmatic issues as well. The simple fact is the x86 instruction set is huge. And we're not talking about like tens or hundreds of instructions, but depending on how we count and how many of the different instruction extensions, like SSC and SSC2 and whatnot, you count in, you can reach up to thousands of, I've even read numbers like 6,000, for example. So it's a lot, and for every single of these instructions, we need to make sure that our mapping to the ARM code is actually correct. It adheres all of the corner cases that could come up, especially in regards to things like overflows. You could imagine how things get tricky there and maybe not so obvious as far as the specification is concerned. And we still need to make sure that it all runs fast, because we don't want to have a slideshow. We want to actually use the applications that we emulate. And for that, we need a fast implementation of this whole thing. Despite this massive task, FEX doesn't lag behind other proprietary solutions like Rosetta for Apple hardware or Prism for Microsoft hardware. As a matter of fact, the AVX and AVX2 instruction sets were first implemented by FEX. And to be fair, Apple gets an honorable shout out here because they were kind of neck on neck with us as far as the with the hardware accelerated implementation goes. But yeah, FEX was the first one to have like a software powered AVX and AVX2 implementation, and I think that's really, really cool. No talk about x86 emulation would be complete without a mention of the ugly, ugly memory model of x86. To illustrate what the problem is, I've prepared, again, a very simple toy example. We have 2 threads in our program, and the first one is just trying to get the second thread to compute a result. So for that end, it's just setting some state to 0, like the actual result, and a done indicator flag. And then it's just sleeping until the done indicator flag changes its value from 0 to something else. The second thread then computes the answer to the universe and everything and stuff, which, as you might know, takes a while. And after that, it sets the done flag to 1. The other thread will then wake up and print the result. And now the question is, what does it print? Naively, you might expect 42. In reality, that is exactly what happens on x86, but it is not necessarily what happens on ARM platforms. And why is that? Well, there's an intuitive assumption that we make here, and that is because the done flag is set, all of the writes to other variables would also be visible in the other thread. But this is not actually a guarantee on ARM platforms. On ARM platforms, what you could see instead is that the observed effect is that first done gets set, and then the result gets assigned. And at that point, it obviously would be a race condition, so the thread 1 might wake up first and print the still outdated result variable. So it's printing 0 in that case instead of 42. This is extremely difficult to resolve from an emulation perspective because we still need to adhere to the x86 semantics. So there's multiple different things we can do. The brute force approach, just make all of the memory operations atomic. There's a huge performance loss. Basically cuts performance into half, at least, for most games. That's not something we want. There's a few tricks you can use. You can take some inspiration from the .NET framework, for example, which uses a thing called half barriers. That helps a little bit, and also there's ARM instruction set extensions like LRCPC. Again, those help a little, but they don't fundamentally solve the problem. We have kernel patches that reduce some of the overhead. It doesn't solve the problem entirely. So at the end of the day, you need to combine multiple different approaches and then sprinkle a few smartly chosen heuristics on top of it. For example, one heuristic we have is specific to Unity games. There's a really, really fun pattern that we observed in that there is a circular buffer that is used for, I don't actually remember what, but it's used by every single Unity game out there. And what we can do is we can just match something like relative stores with an offset of exactly 61 bytes, which is exactly what that ring buffer is using. And if we do this, we can disable these strong memory model semantics for everything else. And it's a massive performance boost for those Unity games. It's a bit of a hack, but just because it so consistently works across such a wide range of the library, it's really worth it in this case. But yeah, the bottom line is there is no silver bullet here, unfortunately. Yeah, so this is all there is to know about the binary recompiler, at least on a very high level. I'm obviously glossing over so many details. What about the kernel layer, though? So there's a couple of different things that FEX needs to take care of here. First of all, the game is expecting to be able to launch threads, and those threads should look like on an x86 kernel. So when you catch like seg faults, so crashes, for example, actually some game engines expect to be able to recover from crashes. This is how they do garbage collection. It's completely ridiculous, but it's fast, so they do it. We need to be aware of this. We can't assume that if we observe a crash, that FEX crashed. No, we need to be aware of it. We need to handle those crash handlers and notify the game of it so that it can take care of it as it would expect on a native x86 system. There is the file system layer, which the game might be trying to access x86 libraries on a system, and it wouldn't expect to read an ARM library instead. So we need to do some redirection for file system accesses in that case. There are system calls that we need to wrap because the ABI doesn't quite match, so the way that an application prepares parameters and then ultimately calls a system call, for example, to allocate memory or different things. That's a different mechanism on x86 and ARM, so we need to wrap every single system call and decode it manually and then invoke the corresponding ARM system call using the right mechanism correspondingly. That's pretty straightforward for the most part. There are a few tricky corner cases, but it's still a lot of work. There's hundreds of these system calls. So you can start to see a pattern. x86 emulation isn't magic. I mean, maybe it is, but it's also a lot of work, so sadly. And then the final piece that I mentioned before is the GPU driver. Thank you. The GPU driver, which simulated to the system calls, there are differences in how that is actually being accessed that we need to take care of. So all of that we subsume under a kernel compatibility layer that sits on top of your ARM Linux kernel and makes the system look like an x86 system. I'm going to skip through the, like I had prepared a couple of detailed slides about how system call wrapping works. If you're watching offline, you can take a look, but I think I summed it up quite nicely. Could you please work? Oh, this is amazing, I love it. Okay, it recovered. So if you recall the old diagram, there was one layer that only one layer actually that we ignored so far, and that is the one with libraries. So the game engine, the graphics API, and the base libraries. they are not actually all that different from the game code itself. As far as FEX is concerned, they are just one huge blob, one huge system, one huge complex system that's interacting with each other, but it all goes through the interface of the kernel or through the x86 recompiled code. So for the purpose of FEX, it's just one thing. We can emulate all of it without really any special handling to that end. And so we can draw a nice separating line between these two layers of the diagram. And we can see we really just have the unmodified x86 software. We don't need to go through the entire game library and port each game individually, but rather we have one universal solution that makes it all work on ARM hardware that is just pretending to be an x86 system. And that's essentially what FEX is in a nutshell. But there's more. This is how you can implement this whole thing and it will work. But there's just two more little tweaks you can do to make things run a lot smoother, even on top of that. And that is code caching and library forwarding. Library forwarding is one realization that we had. The Vulkan libraries are actually really, really expensive to emulate. And we kind of already have them on the system, so why don't we just take what the application is doing as far as function calls into Vulkan and just forward that into the corresponding ARM Vulkan system? And that's exactly what we can do by hooking into any accesses to the Vulkan library and injecting our own little Vulkan bridge in between that. The Vulkan bridge doesn't do a lot. It just ships basically a little bit of magic to do just what I said. It redirects every single Vulkan library call into the corresponding ARM Vulkan functionality. And this has two benefits. The first one is we don't need to go through the costly emulation of the original Vulkan library. So that saves recompilation time, and it saves the overhead of the blown up ARM assembly code that we generated. But we're also entirely sidestepping the kernel compatibility layer because we're now talking about native code that doesn't need to go through this layer anymore. And the other thing that's actually quite fresh off the press is code caching. So with code caching, you only need to use the recompiler on the ideally. You only run the recompiler during the first run of your game. During that first run, FEX will keep track of all the blocks that have been executed, all the locations in the code that the game was trying to run. And on the next run of the game, FEX will pull ahead all of the compilation processes that previously were done on the fly, and it will collect one huge binary and save it to disk so that subsequent runs of the game do not need to use the recompiler anymore in a lot of cases. And the benefit of that is you get much faster loading times, and you have a vastly reduced risk of micro-stutterings while playing the game. The last thing you want to happen is that you're playing Fortnite, and all of a sudden you're losing like 5 frames of the gameplay just because you're meeting a player that wears a skin you haven't seen before. And that's exactly the kind of problem that code caching hopes to resolve. All right, I hope this wasn't too heavy. There is maybe now a time for a little bit. My slides are not cooperating. There we go. A little bit of demo time. Do you want a demo? Do you want to see this actually in action? Joke's on you. This is the demo. I'm actually not sure if the breakages we've seen are due to the what I'm just going to show you in a bit, or due to the slide framework. But yeah, so as you might have guessed, this presentation is actually a web slide deck that's running in Firefox. And hopefully I can exit full screen mode. Thank you. And this Firefox is actually an x86 build that I downloaded off the mozilla.org website. And I was giving it a try for this. And I was giving it a try for this presentation. I didn't actually know if it was going to work. It just did. And what I like about it is, it nicely illustrates one of the qualities of FACS, that this is really well integrated into the system. If I'm, oh, I don't actually have a taskbar set up on this monitor. But so this thing is actually showing up in your normal taskbar, along with other applications. If I'm dragging the window handles, you can see my silly wobbly windows effect. It's just like a native application to all intents and purposes. It even has a GPU acceleration, and I wanted to open one of these. Let's see if I'm picking it. Oh no. Love it, love it. Okay, this is my time to take a drinking break. So even that works, apparently. And yeah, we're getting GPU acceleration in the browser, so amazing. Are you ready for more? I just need to find where I had it. This might take a while to start up, but yeah, you can see this is actually a ThinkPad X13S, a really nice piece of hardware to develop on. And it's shipping 4 performance cores and 4 efficiency cores, all of them ARM-based. And hopefully, in just about any moment, we will see something pop up on the screen. But, oh, popping up on the other screen, like popping up on the other screen and popping up again. So we have a Steam library. And we can run games directly from the Steam client, as you would ideally expect. And it's again launching on the wrong monitor. I hope I can, yeah, I can drag it. Please. Well, okay. So this is my window manager acting up. We'll work with it. You can see the important bits. Yeah, so this is really just a Linux multi-monitoring thing now, not FACS. I just really wanted to take a moment to show you that FACS is also capable of running 3D games at fluid frame rates, as hopefully we'll see in just about a moment, once the loading screen passes. There we go. I have no idea what I'm doing here. Yeah. Is it? It's, yeah, okay, it's, the frame rate is, so this screen is laggy. I'm not sure if this one is. Slightly, so it's supposed to be fluent, and again, I'm blaming multi-monitoring here for this one. But it's still playable, so yeah. 3D games work. There's also people who've tried like actual AAA games like Cyberpunk, Doom Eternal, Ultimate Epic Battle Simulator 2. I don't know. I've heard about Cyberpunk. I don't personally play those games, but apparently they work in FACS if you are curious. I'm just going to go back into the presentation and finish up really quickly. So, is FACS actually used in practice today by anything? Yes, it is. The Asahi Linux project, who's porting Linux to Apple devices, was one of the earliest big adopters of FACS. They're using it to enable Steam gaming, like I just showed you, on these devices out of the box. They have a lot of really fun extra challenges. Sven is going to give a talk about this on the last day of Congress, I think, So make sure to give that a watch if you're still around or have access to the internet. Parallels Desktop unexpectedly started using FEX at some point as part of the x86 emulation backend. They wrote a nice blog post about this. The Codeweavers folks, who's the company driving forward Wine development, integrated FEX into their project as well. And well, you might have heard about this one. Valve has been working on a new VR headset called the Steam Frame, and FEX is going to play a nice role in there to enable x86 gaming, x86 VR gaming on this new device, released for scheduled for release for next year. Perhaps this is also a good point to disclose. They've actually been putting actual money into this project, so a couple of developers of FEX, me included, were actually paid to improve FEX. So none of this would have really been possible without Valve's monetary support. So thanks again a lot for that. The elephant in the room. I've just been talking about Linux games so far. I'm glad nobody complained. So what are we actually going to do about Windows games now? You might now not try to run Super Kitten Adventure anymore, but Puppy Simulator.exe, which is a .exe, so you know it's a Windows game. The normal approach on Linux for this is to just use Wine and its re-implementations of the Windows libraries. But we still, and those run on top of your x86 Linux libraries, but we still have the problem that our whole underlying system, the kernel, the CPU, and the libraries are ARM. But FEX is accurate enough that you can use it as a layer in between that to build an even more complex stack. So your recompiler and the kernel compatibility layer are powerful enough to run Wine, which then can run a Windows game, just like that. And that is actually exactly the setup used by Asahi Linux, but there is a different approach, in fact. And how that works becomes apparent if you have two ideas. The first one is Wine, the runtime part of Wine, is just that. It's a runtime. It doesn't really need to be x86 for a strong reason. So we might as well start and just move it down the stack and recompile Wine as an ARM executable. I'm skipping over many steps here, but conceptually that's the idea. And then the other trick that we're using is we're not compiling to normal, quote-unquote, ARM64 code, but rather to a variant of it called ARM64EC. The EC stands for emulation compatible. The idea here is that the recompiler output, we're in full control over it, so we might as well make it a little bit easier for x86 code to interface with it. And what this allows us to do is to shift the output of the recompiler up several layers in the stack so that it basically only applies to the game's code anymore. And the underlying Windows libraries, because we already re-implemented them anyway, we can also recompile those from x86, not from x86, like we have the actual source code for them because we re-implemented them, so we can just compile them to ARM64EC. Again, skipping over steps here. But what that allows us to do, we have native code providing the functionality of Windows library now, so we don't need our x86 Linux libraries anymore. We also need to, we can throw away the entire kernel compatibility layer. We only need a basically small shim that almost isn't even worth mentioning anymore. And so with that, the diagram becomes a lot more simple. Contrast that to the previous approach, which, so the two don't really have a name, like one is just x86 Wine running in FEX. And the other one we sometimes like to call Wine on ARM in analogy to Windows on ARM. It's kind of the same thing. And indeed, like this whole ARM64EC dance isn't something we came up with, so I will not take that credit. It's actually the original thing that Microsoft used when bringing up their Surface laptops. And indeed, I could talk a lot about this, but this has been much better summarized by Darek on his blog, where he goes into all of the nasty details about how this mechanism is working on Windows, and it's a tremendously valuable resource, so if you want to learn more, I recommend checking that out. The bottom line is, we get a much simpler emulation stack with this approach, while at the same time getting better performance out of it, because there's so many fewer components that we need to emulate in the first place. None of the stuff here needs to run prefix anymore, so that's why that's working so much better. We're still having some issues actually getting this set up to users, but this is something we're working on. Hopefully we'll get there and provide a convenient solution for that soon. But yeah, with that, it opens the question, what comes actually next? And I'm going to gloss over this really quickly because I want to leave some time for questions. Basically, we have a product launch coming up. There's going to be so many testers, and I hope that Fex is going to surprise everybody in how well it actually is already working. But inevitably, there's going to be issues that come up. So we're going to work on improving compatibility where possible. We're going to improve performance to make sure that everything's working as smooth as people expect. And yeah, that's the plan for the next months. And with that, there's one last thing I need to mention these times and days. We don't use AI. Not out of principle, not out of principle. It's just not a problem where it helps. There's just no reason to use it. So neither the presentation used it nor affects itself in any of its code. That's all I have. Thank you so much.
Wow, what an awesome project. Thank you for presenting it there. Unfortunately, we do not have any time for questions left. I heard that there is a lot of questions on the internet, so maybe can you tell us, for the people here in the room, where they can find you if they have any questions after the talk, and also to the people on the internet, how they can ask these questions to you.
So for the people in the internet, thanks for watching the stream already. Best place to reach me is probably Mastodon or Matrix, same moniker, neobrain@matrix.org. For the people who are still around, I am probably gonna head back to the hotel right after this thing, but
people in the room, please keep quiet a bit until we're completely done. Thank you.
For people at Congress, I will probably be hanging around the Dolphin Emulator Assembly, but if I'm not around there, just hit me up on Mastodon or Matrix so we can still chat in person here.
Okay, thank you.